Olá. Tudo bem?
Okay, so I think we can start. First of all, introduce Professor Thaisa Bergmann. It's my great pleasure. So she did her undergrad in physics at the Federal University of Rio Grande do Sul, followed by a number of postdoctoral and research positions in the U.S. University of Maryland Space Telescope Science Institute, the Rochester Institute of Technology, and the Harvard Smithsonian Center for Astrophysics. She's a professor at the Federal University, where she's also the head of research at the Astronomy Department, level 1A researcher from CNU. Professor Bergmann has received a number of scientific honors, including the Scopus Prize from Elsevier and the L'Oréal Prize for Women in Science. She's a permanent member of the Brazilian Academy of Science and also a member of the Brazilian Astronomical Society, the World Academy of Sciences, and the International Astronomical Union. Her research focuses in extragalactic astrophysics, in particular supermassive black holes and their role in the evolution of the universe. Precisely this topic of the colloquium that she presented to us. So please let's welcome Professor Thaisa.
Thank you very much for this invitation for me to present my work here. So I do research on supermassive black holes, and I want to tell you about their role in the evolution of the universe. This year is particularly important for supermassive black hole science because we had the first image of the event horizon around a black hole in the center of galaxy M87. And so this you maybe saw in the news, right? This happened 100 years after the first test of general relativity that happened nearby here in Sobral in 1919. So 100 years was commemorated last May in 2019, this year. 100 years of this test that was done during a solar eclipse in Sobral, where the test consisted in measure the deviation of the light of a star that was around in the direction of the sun. And during the eclipse, the light of the sun was blocked, and you could measure this deviation that is largely exaggerated here, but this was then the first test of general relativity. Let's see. I have a movie here that I like to present. I don't know if the lights can be turned down, turn it off. Maybe off just for the movie. This is about 1 million galaxies in the near universe, and we are traveling through their distribution as measured with the Sloan Digital Sky Survey. And the positions, the relative position, are well represented as the shapes of the galaxies. So if we could travel faster than light around the universe, nearby universe, we would see that. And the music I added because I love so much. So this, then you can turn on the light a little bit. So this is only 1 million galaxies, and we know that the universe, the visible universe, that at least 100 billion galaxies, okay? And in each one of them, there is a supermassive black hole in the center. Maybe not all of them, but every galaxy that has a bulge, a central concentration of stars, has a supermassive black hole in its center. So they are important to consider. This is just to remember that we are our little blue planet orbiting our sun, and the sun is one of the 100 billion stars in the Milky Way. We are in a small group of galaxies, and then our group is part of a big cluster that we call the local supercluster center in the cluster of Virgo. Okay, so what I'm going to talk about, just to introduce what is a black hole, talk about the stellar and supermassive black holes, how we observe them, and then about the role of the supermassive black holes in the evolution of the universe. My work is in the feeding and feedback of supermassive black holes, and then conclusions. So beginning in the definition, what is a black hole? Maybe everybody knows, I don't know. But in any case, to talk about black hole, we have to talk about gravity. So we know this classical definition by Newton of the force of gravity. And if you have a big mass m and you put a probe mass small m in the potential of this big mass m, you have this force that is proportional to the big mass m and inversely proportional to the distance square. So we can increase the force, the gravity, if you have, if you increase the mass, but also if you decrease the radius, okay? And the black hole is the limit where you increase the mass and decrease the radius, so that in a simple way we can say that the escape velocity becomes equal to c, where c is the velocity of light. So not even light can escape. And this is why it's called a black hole, okay? If we use general relativity, then according to Einstein, the gravity is curvature, introduces a curvature in space-time. And then in the vicinity of massive objects, you have not only the objects, but also light follow curved paths, okay? So this is the Einstein equation. Yeah? So the mass and energy introduce a curvature in the space-time. Okay. Okay. If you increase the gravity, for example, you begin with the sun that introduces some curvature in the space-time. And then if you want to increase the gravity, you can go, for example, to a white dwarf, which is a star with the mass of the sun, but the size of the Earth. Okay? And then you can increase the gravity, increasing the curvature in a neutron star that has 10 kilometers of radius and the mass of the sun. So the curvature is very big, but the limit is the black hole, where you have this event horizon from which nothing can escape. So the event horizon of a black hole, this is an artistic representation. So it's defined by the Schwarzschild radius, which was derived by Schwarzschild, solving the Einstein equations. And the Schwarzschild radius, we can say that define a surface of no return. So if a matter of light gets trapped there, it won't never come back. Okay, and this radius is just proportional to the mass of the black hole. and this is the gravitational constant and the velocity of light. Okay, so we can easily calculate, if you have a mass, you can calculate the Schwarzschild radius. So if you want to make the Earth transform it in a black hole, you have to compress it to 9 millimeters radius, okay? The sun, 3 kilometers. Okay, so the sun has 700,000 kilometers. You have to compress it to 3 kilometers, then you have a stellar black hole. And we have a supermassive black hole, for example, in the center of our galaxy, the Milky Way, that has 4 million suns, the mass of 4 million suns. And then it's just scale 4 million times 3 kilometers, and you have 12 million kilometers for the event horizon of the supermassive black hole in the center of the Milky Way. Okay, so this is the theory, but do we observe in nature? Let's define the two main kinds of black hole. Maybe we have intermediate size also, but the two main divisions are stellar, which is the end product of a massive star. When the star evolves, it passes to different stages, red supergiant, and then in stars more massive than 10 solar masses approximately, then the end of the stars is the explosion of a supernova. But before the explosion, there is an implosion. The energy produced in the center cannot halt and cannot support the external part of the star that falls into the core and produces an implosion of the core. And then you have a black hole. You can have a neutron star, but if the star is very massive, you produce a black hole. Okay? So stellar black holes are the end product of massive stars. So these are artistic conceptions. And you can see these stellar black holes when you have something orbiting it, okay? Because if it's a black hole, you don't see light unless you have something being captured, something in orbit around it, okay? So, for example, one example of stellar black hole in the Milky Way is Cygnus X1. It was discovered as a star emitting X-rays, and we discovered there is this is artistic illustration. There is a blue giant star, but when you observe its light, you conclude that the star is doing this. Back and forth, in an orbit around something that you don't see. Okay? And you can calculate the mass of the object you don't see, and the mass is like 10 solar masses, more or less. Okay? And as we know, this is just to show the region. This is an actual image of Cygnus X1. So what we see is the light of the blue star. And because we know how many stars we have of different masses, we estimated that there are about 100 million stellar black holes in the Milky Way. And in other galaxies. Right? Okay, so this is for stellar black holes. Now let's talk about the supermassive black holes. Okay, how do they form? We believe, okay, that they formed. First the masses. They have masses between 10 to the 6 to 10 to the 9 solar masses, 1 million to 1 billion solar masses. And they are in the center of the galaxies. And we see, I'm going to talk about how we see them. We see the quasars, and we now know that the quasars are supermassive black holes capturing matter, okay? And we see them to very large distance in the universe, And the most distant ones have been formed 10 to 13 billion years ago. So this would be a representation of the evolution of the universe. Here is the present day. The universe has 13.7 billion years of age. Okay? So the beginning is the Big Bang. Then we have the Dark Ages. And then we have the first light in the universe. This is something that we are trying to pin down with the next space telescope, the James Webb Telescope. But the peak activity in the universe, when most stars have formed and most black holes are observed, is about 3 billion years of age of the universe. So we are looking back into the past, as far as when we go far, the light has traveled many billion years to reach us. So we are looking the past of the universe, and we see that many quasars are around here. And we have some record-breaking quasars, and more or less they have the same redshift as the first galaxies that we see, the most distant galaxies that we see. So all these points that the quasars and the galaxies practically formed together in the first billion year of the universe. And as I mentioned, this peak formation is when the black holes grow more and when the stars form at a higher rate in the universe. So we believe that they form together with the galaxies. Okay? So it's not that clear. We cannot witness the formation of a supermassive black hole. So we rely on models, and models have two options. Form stars, and then the stars in the center of the galaxy, because they are too close, they merge and form a black hole. Or maybe the black hole, when the cloud that will form the galaxy collapses, maybe in the centers already there are conditions to form a black hole. So these are models that are being developed. So how we discovered that there should be black holes in the center of galaxies? The first indication is the quasars that are the quasars that I mentioned before. The quasars were discovered first from their emission in radio. And in ground-based telescopes, when we would look at quasars, it looked like a star. So this name is from quasi-stellar object, because it looked like a star, but the characteristics were different from a star. And so it looked like a star because the Earth atmosphere blurs the light of the objects that come from space. The light comes from space. And so we couldn't have the necessary definition to see what we could only see with the Hubble Space Telescope. And the Hubble Space Telescope showed it, because the Hubble has a definition that 100 times better than the telescope seeing without adaptive optics of the time. So Hubble had much more resolution elements. And Hubble could see that, the quasar, it's like a star in the center, but you could see what the galaxy around it, okay? So Hubble showed that, quasars are galaxies, actually the nucleus of galaxies, okay? And why they are so bright? So the explanation is the following. Cannot be stars, because the stars are responsible for the light of the galaxy. What shines more than the galaxy? The quasars, the brightness of the quasar in the middle of the galaxy sometimes is brighter than the whole galaxy. So what is brighter than a star? Or many stars, actually. So the idea is the following. When you have a black hole, the mass is captured and form an accretion disk. Why is that? Because usually you have angular momentum, and the gas forms this structure that stays rotating around the black hole. And they released gravitational energy because the supermassive black hole is so compact and the gravity is so strong that there is a strong release of gravitational energy. And in the disk, the disk acts like a generation of radiation because the disk is made of plasma, first gas, then plasma, because it gets ionized, and it gets hotter and hotter, and began to emit continuous radiation. And sometimes you have winds from the disk and jets from the inner border of the disk. So if you calculate the efficiency of the energy release in the accretion of mass, so if you calculate the release of gravitational energy from the mass being captured from infinity to the accretion disk, to near the black hole, you conclude that the gravitational energy released is 10% of mc squared. So this is very, very efficient. 10% of the rest mass of the particle being captured is transformed into energy. So to realize that it's very, very efficient, we can compare with nuclear energy, that is the energy released by the stars. So for each mass m, you have 0.007 mc squared. So this is more than 10 times more effective, right? So the generation of energy by a black hole from the capture of mass by a black hole can be considered the most, can be considered the most efficient energy generator of the universe, okay? I don't know if you got this idea. Did you understand? Okay. So if you could use to generate energy a black hole, it would be very nice, because we are now struggling to have nuclear energy to, using this efficiency. A black hole is much more efficient. And I like to make an analogy. How you can have gravitational energy transformed into other kinds of energy. And this is analogous to a power plant, when you have the fall of water moving a turbine and a generator. So the accretion disk would be the turbine and the generator of energy. Okay? So the transformation of the gravitational energy is the same that happens in a waterfall power plant. Okay? The concept is the same. Okay? And I have another movie that shows what we believe is happening. This is also an artistic representation. This would be what happens in the accretion disk. Esse é satélite. This is satellite Swift satellite. This is the Gemini that we use in our observations there. I use Gemini and other colleagues, astronomers also. So this is a simulation. What happens when you have an accretion of matter around a black hole, and you have these ejections that we see in nature, okay? And very powerful. And so now we know about the black holes, and we can see that they have an impact, not only in the galaxy, but also outside the galaxy. So to understand the evolution of the universe, the evolution of galaxy, we have to quantify and observe this impact. Okay? Actually, the models, nowadays, cosmological models of galaxies evolving in the universe have to consider the impact of this feedback from black holes that are associated with the accretion disk around it. Okay, so this is some results showing why we care about supermassive black hole. Okay, so when you have a supermassive black hole active, we have what we call active galactic nuclei, so, in plural, or active galactic nucleus, such as the ones I just mentioned in quasars. Okay? The observations of the universe, of galaxies and supermassive black hole, show this graph here that is called Madal plot, because this guy Madal, an Italian astronomer that works in, I think, in Caltech, what he did was the following. This is redshift. Everybody knows what redshift is? Yeah. Okay. So when you redshift is equivalent to look back time. So when you look to high redshifts, you are looking back in time towards the origin of the universe. So we now have so many observations of galaxies and quasars at different distance that we can make this plot. So what this plot shows is that this would be the density of star formation in the universe. How many solar masses per year are produced per megaparsec cubic megaparsec, okay? I don't know if you know megaparsec, but 1 parsec is 3.20 light years. So it's a unit that astronomers like to use. And megaparsec is 10 to the 6 parsecs, right? Okay, so you can measure the density of star formation rate. So in black, you have this line, which is how many stars are formed per year per megaparsec cubic along the history of the universe. Okay, so as I mentioned, there is a peak at look back time 10, more or less, redshift about 2, where most star formation happen in the universe. But we can also calculate from the AGN, active galactic nuclei, you can calculate from their luminosity, which is the accretion rate of the growth of supermassive black holes. So, by measuring active galactic nuclei, you see that the curves are similar, although the black holes grow at a rate 3,300 times slower. Okay, so you have a coevolution of the black holes in the universe and the galaxies in the universe. Okay, so this shows that the black holes and the galaxies are growing together. Okay, and why there is this coevolution? Why in the universe the black holes are growing together with their galaxies? There are 2 reasons. One is that they feed on the same mass. When you have stars forming in a galaxy, you need gas, and the gas will form new stars. But the black hole in the center also feeds on gas. So they have the same source of fuel, which is gas. Okay, so this is why, this is one explanation. Another explanation to link the two phenomena, the AGN at the center and the galaxy around it, is that there is feedback of the supermassive black hole. And the feedback can eject gas and halt star formation in the host galaxy. Okay. To understand better the role of feedback, so what is the feedback? The feedback from AGN, remember, it's like the quasars, are outflows, jets, radiation, and all these are necessary to include in the evolution of galaxies. So there are many theoretical studies showing this. And this is a representation of the galaxy luminosity function. What is the galaxy luminosity function? Is that how many galaxies you have of each luminosity. So this is the luminosity. The observation shows there are some galaxies, a density of galaxies with low luminosity. Then as the luminosity of the galaxies increases, you decrease the number of galaxies. And this would be observations. But when you do models of galaxy evolution, which call it the cold dark matter models, the theory gives much more galaxies at low luminosity and much more galaxies at high luminosity. So if you construct a universe expanding everything, but with only gravity, you should have much more massive galaxies and much less massive galaxies than you observe. So something is not right if you only include gravity and the expansion of the universe and dark matter and everything. You have to include some feedback to not allow that you have more luminous galaxies and more low luminosity galaxies. So we say that this, in order to bring this red curve to the blue curve, you have to have feedback from AGN. So the feedback makes the gas go away, and you have less stars formed, and the galaxies doesn't become so big. And at low luminosities, supernova are the feedback necessary to decrease the number of low luminosity galaxies that we see. Okay, so we need feedback. So the models now need to put feedback from black holes and feedback from star formation. Okay? And how much feedback you put? It's so we have to measure. The astronomers that make observations like myself, we have to measure this feedback to tell the models what they should put in the models. Okay. The theory shows that if you want effective feedback on the galaxy, you have to have a power of an outflow, for example, if it is an outflow, between 0.5 and 5% of the AGN luminosity. So these are the models give. Okay. Okay, this is something. Okay, so I would like to show a few things about my observations. I finished this year a review where I showed how the gas feeds the supermassive black hole, how the gas arrives to the center to produce the nuclear activity. Okay? So in this review, I have shown that at large scales, 10 kiloparsecs or more, we have interaction between galaxies that produce inflow of gas in direction to the center. Or cold flows, we now understand there is this cosmic web that is gas left over from the Big Bang, and then this is falling into the galaxies. inside galaxies at 10 kiloparsec scales, we have galactic structures such as bars and spiral arms. But then we arrive to 100 parsec scales. We see nuclear spirals and nuclear spirals, disks, and bars. Okay, and then we have now with ALMA at 10 parsec, we are seeing molecular disks and also gaseous spirals. And and 1 parsec, very in the center, we have the black hole, we have an accretion disk, and we have clouds, and we have the torus. So these are clouds orbiting the black hole at high velocities. And the torus is something, a dusty structure that surrounds everything. So we have a sequence of different structures to lead to the feeding of the black hole. Okay? So this is just to show the team, the people that have been working the last few years. Some are already left. And we have a group that we call AGNIFS, AGN, Active Galactic Nuclei, Integral Field Spectroscopy. So integral field spectroscopy, I don't know if you already listened about integral field spectroscopy. It's a new technique, not so new now. I use it for 15 years already or more. And it is some new instrumentation that once we did either image of a galaxy or we did the spectrum of the center of the galaxy, for example. Now we have an instrument that gives a data cube, gives image and the spectrum of each pixel of the image. So you can, for example, if you want the image in a continuum to see how the stars are distributed, you take an image. If you want the image of how the gas is distributed, you take a slice where there is an emission line, and so forth. So it's a very powerful instrument for kinematics, for excitation. So we have everything. It's a three-dimensional, we call data cube. Okay? Imaging and spectroscopy at each point of the image. So this is would be to show what kind of observations we do. The field of view of our IFU is kind of small. So this is let me show. It's one galaxy in particular, and that it has this spiral structure in the center. These are dust in the plane of the galaxy. This is an image, and this is a Hubble Space Telescope image, and then processing this image, you can see the dust. And then this is the field of view of the IFU, and this is the continuum. So this is, we are looking at the inner kiloparsec, 1,000 parsec in the center of the galaxy. And for you to take a look of the spectrum of each point, shows this. For example, all this is a spectrum, flux against wavelength, and you have the absorption lines that are the lines that come from the atmosphere of the stars. Okay, so you have the absorption lines, and you have the emission lines that comes from the gas. Okay, so we have to separate the contribution from gas and from stars. Okay. And then we use Doppler, the Doppler effect to measure the kinematics. And these are the velocity fields. And I realize that maybe it's a bit complex for you to understand. But what we have here is the velocity field of the stars that we got from the absorption lines. And we have a very low amplitude rotation. Blue means that the gas is coming towards you. Red means that the gas is moving away from you. So this is This is a rotation field, okay? Gas coming, gas going. This is rotation. And we fit a model because it's a bit noisy, and this is the model, okay? So the gas is coming, going, coming, stars, actually. Here's the stars. Coming and going, 440 kilometers per second, okay? And when we look at the gas, so the stars do this is the model. When we look at the gas, this is one emission line, we see that the velocities are much higher. Instead of 40, we have 200. So the gas is going much faster. So, and you see that the orientation is different. The gas is here, the blue shift, and the red shift is there. And we could see a correlation between the structure of the velocity field and the spirals that we see. So we concluded that this gas, when you subtract the contribution from star, this gas is coming towards the center from the near side and from the far side, following these nuclear spirals, okay? And so we could calculate the velocities and the mass inflow rate. So that was what we could say a resolved study of the kinematics, and I have this result that are unresolved. So this unresolved is that you cannot measure the position, comes from a point source. So this was the discovery that led to many works over a number of years here. And this was 2 PhD students that worked with this data. And this is a galaxy, NGC 1097, where I was studying the movement of the gas in the inner region. And when I took a spectrum from the nucleus, I discovered the light from an accretion disk, or the outer parts of an accretion disk has only emission in these outer parts. And I want to show you how I did the discovery. So at that time, I was doing long slit spectroscopy. This would be the inner region of the galaxy, and this is a slit. And you can extract spectrum from A, that is the nucleus, and B and C, that is to the side of the nucleus. So A, the nucleus, show this spectrum. As you see, there is a lot of absorption lines from the stars, and there are emission lines from the gas. And B and C, it's only stars. So I use this light from stars to subtract the contribution from the star and isolate only the gas emission. And then what I've discovered is that beside these narrow lines that are gas that is in orbit in the star, I saw this what I call double peaked line. So this is the H-alpha line of hydrogen, and you can see these double peaks. Can you see the double peaks? So this would be, there is a narrow H-alpha, and there is a very broad H-alpha, okay? And when you calculate the origin, why it's so broad, and then you can make a model, as I did here, that in the next, I have a movie showing that. So the double peaked profile is that thing. And so the red is the model of this outer part of the disk rotating, and you have some asymmetry that makes the peaks going up and down. And so this is some monitoring a few years. And in the last observations, it was a little bit low. These are the dates that I did this monitoring. So I'm actually seeing a disk. Actually, it's the outer part of the accretion disk, because this to produce this profile, you have to have emission line, okay? The emission line needs temperature 10,000 degrees. You have to have recombination. It's a recombination line, H-alpha. So you are not looking at the inner part that is plasma, that is all ionized gas. You are looking at the borders, around the borders of the accretion disk. And I saw how the gas was behaving there, okay? So I could do modeling. This velocity, it's about 10,000 kilometers per second. The highest velocity is here. And it is this double peaked profile is due to gas rotating then in a ring in the outer parts of the accretion disk when the gas becomes recombined, when there is a recombination to produce the emission lines. Okay. I'm back. And I did more. Now, that was one source. Now I realized that these disks are present in many, many other AGN. Okay, so this is just to illustrate. For you to have an idea, the angular radius of this structure, an average angular radius, it's 10 to minus 9 radians. Okay, so it's very, very small. You cannot resolve. You cannot see the image of. It's only I saw this structure in how you say in the velocity space, not in the image space, right? But then, if you wanted to see the image of that accretion disk, of that outer part of the disk, we call sometimes the broadline region. Okay, then you have to use a technique called interferometry, and there is an instrument called gravity, led by the Genzel group in the Max Planck Institute for Extraterrestrial Physics, where they use the 4 8-meter telescope of VLT. These are the 4 VLT telescopes. Each one has 8-meter mirror. And they combine, the beam combiner instrument is this one, stays here. So you combine the light of 4 telescopes, 8 meters each. And then you simulate a telescope with an aperture that is equivalent to the distance of the two most distant members of the set of telescopes. Okay, so with this instrument, they are beginning to resolve this outer part of accretion disk. So this is being done as we speak. Okay, so it's an ongoing project because, as I said, the accretion disk, that broadline region that emits that disk that I mentioned, so far we had only seen in the velocity space. We use a spectra to do modeling and infer which is the structure. That is, the structure is a ring. Okay, yeah, and this ring is the outer part of the accretion disk. But if you want to have an image, you have to do interferometry, and this is the same technique that was used to make the first image of the event horizon of the black hole in M87, right? So to the disk, the outer part of the disk that I mentioned, it's about 1,000 times the Schwarzschild radius, which is the event horizon radius. So if you want to image the event horizon, you have to have intercontinental interferometry. And this is what the event horizon telescope is. They use the combination of different telescopes spread around the globe, Hawaii, United States, Chile, and Antarctica. And so we used it, and they observed it in April 2017, several targets at this wavelength. For you to understand what they need to achieve is 10 to minus 10 radians to see the event horizon. And they did it with this array and got this image so the event horizon inside here in M87. And then I want to talk a little bit about outflows. And in this sense, I want to advertise a symposium, IAU symposium, that we are hosting in March in Bento Gonçalves, in the south of Brazil, in the wine county. We are going to host this conference. If anybody is interested, I invite you to come. Well, yeah, there is one deadline that passed, but it's just to request support from IAU. And December 10 is another deadline. Okay, so I just show some equations here. Is that what I'm trying to calculate? The power of the outflows. I see these outflows in the AGN, active galactic nuclei, and we are trying to calculate the powers. And it's a very simple equation. We just calculate this would be mass outflow rate. So we see outflow from the inner region of AGNs, and this is the velocity of the outflow. And then the mass outflow rate you calculate from the mass of the gas, the velocity, and the distance from the center. And then the ionized gas mass you can calculate by this formula using the H-alpha line to get the mass of the gas. And so to illustrate quickly, for example, these are using IFU units, integral field spectroscopy again. You have, in this galaxy in the center, we have seen these biconical outflows. And it's interesting that in some emission lines you see outflows. This is the model. This is what we see. And another emission lines that are molecular hydrogen, we see something very different. So it looks like these are channel maps, which mean that you are seeing this gas in blue shift, channels minus 600s until, so this is our blue shifts, gas coming towards you, and these are red shifts, gas moving away from you. So in this case, we discovered there is an outflow in this shape, and the ionized gas that we see aligned in iron show these outflows, and the molecular gas show this ring in the plane of the galaxy. So we measure these outflow rates. This is just to show something that we are trying a little bit more distance. There are nearby QSOs, quasars, at redshifts between 0.1 and 0.5. And this would be the light. These are HST Hubble Space Telescope images. This would be the light from stars. And this is the light from the gas. So you see that the light from stars is more compact, and it looks like we are seeing an interaction of a dwarf galaxy with another bigger galaxy. And because of this, maybe you have all this gas spreading, maybe because of the interaction that I mentioned, producing these outflows. Okay, so we are measuring these things. And we are measuring the outflow powers, and we are now realizing that we tried, each color is one method of calculating the outflow, different geometries, different gas densities, and we see that it varies a lot, orders of magnitude. So it's a very tricky way to try to calculate these outflow powers. And so I'm not going into detail. But many results shows that the outflow rate and outflow powers seems to show some correlation with the luminosity of the AGN. But we have a lot of scatter, and the outflow power depends on the method used to calculate it. Okay, so let me put my conclusions. What are the takeaway points that I tried to show to you? That a accreting supermassive black hole can be the most efficient energy generator of the universe. These instruments are interesting to constrain the process of inflows of gas and feedback also in galaxy. So we can constrain the models of galaxy evolution. We have studied the feeding. We have found inflows on all galactic scales. And 100 parsec scales is that what we've done most of the AGNIFS project. These are the velocities that we find. So very slow inflow, 50 to 100 kilometers per second. Mass inflow rate from 0.1 to a few solar masses per year. And we find a signature of coevolution between the supermassive black holes accretion rates and the galaxy. So we find that the two grow together, but it is already implied by the Madal plot. It's not going. One thing that we are finding regarding feedback, that I'm still working on this subject, is that the gas, the ionized gas, extends to to big distances. But the outflow seems to be more confined to the center. And so these are details that I'm not going to talk about, because I think that maybe it's too much detail for you. We are finding the power less than 1% of the luminosity of the GN, and this implies little effect on the galaxy, but we also found that this calculation of feedback depends on the method. Okay. And we find this correlation if we include more powerful outflows also from the literature. And to finalize, okay. And to finalize, if anybody is interested in my stuff on supermassive black holes, I have a homepage, I have this Facebook, and I'm trying to do some astronomical drops astronomicus, which are little movies that I do explaining one topic in 5 minutes. So I'm enjoying doing this. My son makes the movie, and I talk about a topic. And so it's getting nice, but going slowly. And that's it I want to tell you. Thank you very much, and if you have any questions.
Perguntas, questions. If you feel more comfortable, you can ask in Portuguese.
Hi, I have a kind of general question about the supermassive black hole, the image of the supermassive black hole. I'm just wondering, because it's not my field, if you can give some example of what kind of improvement that image can bring or brought to the models. Can you say some examples? Considering the constraints or something.
Yeah, you know that I think that the image showed that the models were right. Because in the beginning of my presentation, let's see. The beginning of my presentation, I showed this thing that is the most recent. I got this simulation of a researcher from the Goddard Space Flight Center. And this simulation was done after the image, okay? But it's very similar to the simulation that was done for Interstellar movie, right? It's the same, the image. Very similar. So it shows that is more or less what it was expected. I think it has to do, the difference has to do with the inclination of the accretion disk. Okay, so because this, the accretion disk is seeing edge on, and if you see more face on, maybe it's more similar. I would say that it gave some constraints, but showed that the calculations were correct. Okay, so it was not something very unexpected. It was more expected than unexpected, right?
Thank you for your wonderful talk. I have a curiosity and a question. If you can go back to that slide, you talked about the radius of supermassive black holes.
The radius, the Schwarzschild radius?
Yes, exactly. My curiosity on that is, how can angular momentum change those numbers?
You mean here? You mean?
Mm-hmm. In nature, not
this would be like a Schwarzschild black hole, as we say. And if you have a Kerr black hole that is rotating, then these numbers change a bit. Okay. Actually, the numbers that change is the radius of the accretion disk. I think the Schwarzschild radius. So if there is some theoretician about black holes, maybe can answer better this question. But I know that, for example, if you have a rotating black hole, then the disk can go further in, the accretion disk.
Can you show me again that image of a galaxy with, it was a slide only with a galaxy.
The galaxy.
It had some jets going in and...
Oh, no, not this one.
No, not this one. Going up and down. Maybe it was that one.
Oh, there was the end of the movie, maybe? Or...
Oh. No.
It was not this one, right?
Yeah, because I don't know, I'm not sure how you call it, but it was a galaxy with like some jet going up and down. And my question is, why that direction that seems to be on the axis of rotation? That is my question.
Well, this, maybe that image you mentioned is appeared in the end of the movie, the one little movie that I showed, that you have, when you have an accretion disk, it's plasma, and usually you have an amplification of magnetic fields that are frozen in the plasma. So as the gas rotates more and more rapidly, nearing the velocity of light, the magnetic field gets amplified, and in the center, you have a very strong magnetic field that can accelerate particles along the lines of the magnetic field. That it's like the solar flares, you know. So it's like a flare that comes up, and you can accelerate, and you make a jet of relativistic particles that go away from the galaxy and reach intergalactic distance. Okay, so this is related to the magnetic field that gets amplified in the accretion disk, and this is observed in radio. So you see that there are very spectacular radio galaxies that have jets that go to several hundred kiloparsecs. The distance between, almost the distance between the Milky Way and Andromeda. You have jets that go away very far.
Hello, thank you for the presentation. I have a question about the nature of those black holes. Could those black holes be formed by dark matter, for example?
Yeah, the relation between the black holes and dark matter is, there are some studies that show, for example, because the mass of the gas, the mass of the galaxy, we know that you have 6 times more dark matter than the baryonic matter, right? And I know of some studies that they found a correlation between the mass of the dark halo of dark matter and the mass of the black hole, saying that there is more fundamental than the correlation between the mass of the bulge of the galaxy and the mass of the black hole. But the detail of interaction between the black hole, if they're capturing dark matter, I couldn't tell you. Okay.
Thank you.
Mm-hmm.
Any further questions?
On the picture of the black hole, if the same interferometry technique was used with telescopes orbiting all the planets or traveling outward our solar system, would the resolution increase?
Oh, if you mean if you had some use larger distance?
Yes.
Yeah, sure. Yeah. But the problem is the technology, because already to make that image, they had to use telescopes all around the Earth, okay? And the internet is not, does not have capacity enough to via internet to connect all the data. They had to bring physical disks to Max Planck or another place, can't remember now, but for example, Max Planck, to combine the signals from all the telescopes together on site. Okay, so the technology for that is still far away, I think. But in principle, the idea is that if you want to see a small thing, a small detail, you have to have a long baseline and maybe also long wavelengths. So the wavelength that they used to make that image was 1.3 millimeters. Okay, that's much larger than visible light. So the technology is better, because you have to have the precision of the order of the wavelength, okay, of all the mechanical parts. And the data handling is very complicated also, because I've been to ALMA, which was Atacama Large Millimetric Array. That is only one set of antennas that was used for the Event Horizon Telescope. And ALMA itself has a big building full of computers to synthesize their signal that are 66 antennas. So it's like one computer per antenna, and so you have the 666 computers, and you have to correlate all their signals. It's a complicated technology, but the idea is correct.
Thank you for your nice presentation. I have one question. As I understood from your presentation, you are more interested in AGN feedback. I mean, one of the effects of AGN feedback. Basically, AGN feedback has two effects. Either it halts star formation rate, or it even triggers, right? Oh, yeah, that's true. But you didn't talk about as it triggers star formation. Because if you consider this case, if you go to the figure that represents the number of galaxies to luminosity, you are trying to fix the difference in the theory and observation, right? To fix that, you are looking for AGN feedback. I mean, you are considering at AGN feedback halts star formation. So you are looking for AGN feedback that possibly halts star formation, so that the number of galaxies, I mean, so that the number of galaxies with low luminosity, I mean, so that you can fix the gap, the difference between observation. What about, but AGN feedback also triggers star formation. So how you solve this? Okay, yeah, it's something that I didn't mention, because the feedback usually is negative. That we have observed more negative feedback, which is the AGN, winds and radiation, blows away the gas, then halts star formation. But some recent results, Maiolino et al., they found occasions in which the outflow encounters some clouds and triggers star formation. So there are some cases.
I think we don't have statistics yet. They try to push more the positive feedback part, but well, then this cannot explain the the model, so they cannot use in the model. But I think that you have positive feedback, but I think it's less common. Okay, so I think that maybe the negative feedback is still higher. This is my opinion, but we need more observations, of course.
Sure, but as long as there is evidence that supports there is positive, positive feedback.
Yeah.
So it really seems to me good to include this idea into the model. The people who are working to develop model.
Yeah. To include the positive
exactly.
feedback.
So last question: which feedback are you interested in? The one, jet associated, or the one from the accretion disk? Feedbacks. Which feedbacks are you interested in?
The feedback from radio jets, for example, it seems to me, I have studied some feedback from radio galaxies, and inside the galaxy, the feedback is not so strong. Okay, so I found very little effect because these jets go away, and it's like a laser beam. They cross through the galaxy, and at large distance in the intergalactic medium, they will push enough material to make these lobes. So it looks like the radio jets are more important for the intergalactic medium, while there are some winds from the accretion disk. The accretion disk is also have some part that is unstable to winds. So these winds, I think are more important from inside the galaxy. So these are the ones that I see more producing stronger feedback. The winds from the accretion disk.
Thank you.
Yeah.
Any final question? No? Well, if not, let's thank Thaisa again.
Thank you.